Imagine for a second, right, that you are sitting in just this horribly tense meeting at work.
Hmm.
You're trying to divide up a shared budget for the quarter across like 5 different departments. You've got your secret agenda, projects you desperately need funded.
Oh, yeah, and everyone else at the table has their own secret agendas, too. Nobody can see the full picture, everyone is getting slightly defensive, and the clock is just ticking down.
Exactly. It is the classic, messy, uniquely human nightmare of negotiation.
But intuitively, you would think that hyperlogical, state-of-the-art AI agents could just solve this instantly, right? I mean,
Yeah.
they don't have egos, so they should be able to crunch the numbers and find the optimal distribution in milliseconds.
You would think so, but it turns out that is not the case at all.
Right, so, okay, let's unpack this, because there's a really fascinating new preprint out of Stanford University by researchers Yao, Zhu, and Hawkins. It's titled, Talk is Cheap, Communication is Hard. And it basically reveals that when it comes to the messy art of negotiating and coordinating with each other, our most brilliant AI models spectacularly fail. They really do. And the mechanism behind that failure, well, it cuts to the very core of how we actually evaluate artificial intelligence today. What's fascinating here is the distinction between two major concepts, which are static grounding and dynamic grounding.
Okay, grounding. We hear that term thrown around a lot in AI, usually referring to like how a model connects its generated text to factual reality, mostly to stop it from hallucinating, right?
Yeah, exactly. And the industry has become incredibly proficient at that, at static grounding. That is essentially mapping a word to a fixed, externally observable context. Like if you prompt a model with an image of a cat, it outputs cat.
Right, or if you ask for the capital of France, it outputs Paris.
Exactly. The meaning is entirely fixed. Our current benchmarks, things like MMLU or standard QA datasets, they almost exclusively test this static one-shot retrieval. They are essentially testing if an AI can state a fact or solve a math problem in a total vacuum.
But dynamic grounding, that's a completely different beast, isn't it? Because that is the interactive, collaborative process of establishing mutual understanding on the fly. It's, two entities talking, monitoring each other's comprehension, repairing misunderstandings.
Building a shared mental model of a problem over time, which is precisely what we do as humans in that tense budget meeting you mentioned earlier. You read the room, you float a proposal, you see the reaction, you adjust your stance, you build an agreement step by step.
But the Stanford researchers point out that current AI benchmarks completely ignore whether models can actually handle this dynamic multi-turn state maintenance. So they set out to test it.
They did. They designed an experiment that forces these models out of their one-shot comfort zone. They built this iterated multi-turn negotiation environment. Basically, it's a high-stakes resource allocation game.
Okay, I love a good game. How does it work?
So two AI agents are given a shared pool of resources. Let's say it's a limited supply of wood, stone, and gold. Each resource has a different unit cost, and the complexity comes from the hidden variables.
Right, because each agent is given a set of completely private projects, right? Like Agent A might need exactly 3 wood and 2 stone to earn 50 points.
Yes, and Agent B might need a completely different combination for its specific projects. They are sharing the pool of resources, but they have these entirely private, conflicting goals.
So to solve it, the researchers give them 5 turns of what they call cheap talk. Basically just unstructured natural language text generation. They get to negotiate with each other before they have to simultaneously output their final purchasing decisions in a structured JSON format.
And the penalty for failure in this game is severe. If the combined demand from both agents for any single resource exceeds the available supply in the pool, an overdraw occurs. The round is entirely annulled and both agents get 0 reward.
It's like going on a high-stakes grocery trip with a friend. You both have secret recipes you're trying to cook, you share one shopping cart, and you have a strict budget. But if you accidentally grab like 1 too many cartons of eggs, the store manager runs over and throws your entire cart in the trash.
That is a perfect analogy. Mathematically, that captures the dynamic exactly. It forces them to coordinate, not just optimize independently.
But wait, if we are dealing with frontier models here, shouldn't their raw computational power just negate the need to even negotiate that hard? If they are so smart, can't they just perfectly optimize their own projects? I mean, the math isn't the limiting factor, right?
No, the math is definitely not the limiting factor. To rule that out, the researchers established what they call the Oracle baseline. They took a single AI agent and fed it all the information, both sets of secret projects, the full resource pool, everything.
And let me guess, it crushed it.
Completely.
Yep.
When operating as an oracle, that single agent perfectly identifies the highest scoring mathematically optimal outcome in isolation without even breaking a sweat.
Wow. So the breakdown happens entirely in the space between them. The gap in performance is strictly a bottleneck in the interactive process of joint planning.
Exactly. Which leads to an important control test. Because if they can solve it alone but struggle together, the researchers had to see what happens if they can't talk at all. So they ran a no-talk baseline where the agents just had to guess the other's needs and submit their JSON requests blind.
Oh man, flying blind in highly competitive scenarios, that must have resulted in catastrophic failure, like they probably overdrew the resources constantly.
They did. Roughly 80% of the time, they overdrew. And their joint efficiency, meaning how much of the maximum possible reward they actually captured, was a dismal 18%.
Yikes. So the unstructured cheap talk is absolutely essential.
It is. When they were allowed those 5 conversational turns, their joint efficiency more than tripled to 63%. It basically keeps them from constantly triggering the overdraw penalty.
Okay, so talk is cheap, but very necessary. And they also tested different models from different companies against each other, right? They used Claude 4.5 Sonnet, OpenAI's GPT-5 Mini, and Quinn 3.5 Flash.
Yes, and the data shows a really clear advantage to crossplay, meaning pairing different models together frequently outperforms self-play, where a model plays against a clone of itself.
That is wild. And when they paired Claude 4.5 Sonnet with GPT-5 Mini, they hit an incredible 79.8% joint efficiency.
Yeah, nearly 80%. And the transcripts from those crossplay sessions are just deeply revealing, because they expose how different training pipelines manifest as distinct negotiation personalities. The researchers actually built a strategy taxonomy to analyze every single utterance.
Here's where it gets really interesting, because they absolutely have distinct personalities. Claude 4.5 Sonnet basically operates as the diplomat. In 53% of its messages, it uses fairness appeals.
Which makes total sense when you consider Anthropic's training methodology. They heavily rely on constitutional AI and reinforcement learning from human feedback, or RLHF, which strongly biases the model toward harmlessness, helpfulness, and consensus building.
It naturally seeks an equitable middle ground. But meanwhile, GPT-5 Mini behaves as the aggressor. In competitive scenarios, it issues explicit threats up to 20.6% of the time.
Right, it uses hardball tactics. That likely reflects a fine-tuning pipeline that heavily rewards strict task completion and objective maximization completely over conversational pleasantries.
And then you have Quinn 3.5 Flash, which acts like the impatient executive. It frequently just submits its final JSON purchasing decisions early, long before the 5 conversational turns are even up.
It's just done talking. But when you combine the diplomat and the aggressor, so Sonnet and GPT-5 Mini, they thrive. Sonnet's fairness appeals act as a buffer against GPT-5 Mini's aggressive threats.
They balance each other out, finding these highly efficient splits that 2 aggressors would just destroy through overdraws. Or 2 diplomats would fail to optimize out of sheer politeness.
Exactly. But even with that optimal pairing, nearly 80% efficiency means they are still leaving 20% of the maximum possible reward on the table. They are only finding the mathematically perfect outcome a fraction of the time.
Right, so to understand why this deep dive really gets into the meat of the paper, it dissects 4 distinct failure modes of dynamic grounding. So we know they are communicating, and it's preventing that 80% failure rate, but cognitive bottlenecks are still happening.
Big time. The first 2 failure modes isolate memory and context. So first, they suffer from a lack of shared interaction history. When the researchers forced the agents to play multiple rounds with shifting partners, basically wiping their context window clean every round, coordination degraded.
Optimum solution rates dropped by 6 to 8 percentage points for GPT-5 Mini and Quinn. So they require that cumulative context to build a rhythm.
They do, however, and this is failure mode number 2, when they were given a stable partner and a continuous shared history, that history transformed into a massive liability.
Wait, really? How does history become a liability?
The researchers call it stubborn anchoring. In 46.5% of the rounds with a stable partner, the agents obstinately repeated the exact same resource allocation they used in the previous round, even when that prior allocation was mathematically suboptimal for the new round's goals.
Oh, it's like human cognitive bias, where we rely way too heavily on the first piece of information offered. It's like going on vacation, right? You find an okay restaurant on the first night, and then you eat there every single night for the rest of the trip just to avoid the effort of picking a new place.
Yes, the cognitive load is just too high to negotiate again. They observed a similar phenomenon in the very first round of negotiations, too, termed first proposal deference. 20% of the time, an agent blindly accepted the very first proposal the other agent generated before any meaningful information about their secret projects had even been exchanged.
Why are these super smart AIs acting so lazy? Why do LLMs fall into this specific trap?
Well, linguists refer to the contribution acceptance cycle. In human dialogue, someone makes a contribution and the listener verifies it, probes it, refines it, and then accepts it. The AI models, however, are driven by the principle of least collaborative effort.
Meaning they over-initiate proposals and drastically under-verify them. Because generating tokens to negotiate a new, complex mathematical split is computationally and probabilistically harder than just anchoring on the first valid tokens already present in the context window.
Precisely. They want to close the loop and output the JSON file. Renegotiating requires just too much conversational effort. If we connect this to the bigger picture, it demonstrates that these models treat the chat not as a space for genuine discovery, but just as a hurdle to clear.
Wow. And this conversational laziness bleeds directly into the third failure mode, which is perfunctory fairness. So the agents defaulted to an exact 50-50 split of the resources 12.5% of the time.
The automated LLM as judge system actually labeled this bottleneck splitting. And at first glance, splitting it down the middle seems equitable, right? But in an asymmetric game, it's disastrous.
Because Agent A might only need wood, and Agent B might only need stone. So a 50-50 split allocates resources they can't even use and deprives them of what they actually need to score points. It's a severe coordination shortcut.
Yeah, they choose the linguistic appearance of fairness over the computational heavy lifting of discovering a reward-maximizing complementary split. This points straight back to their training biases.
Right, because when faced with a complex asymmetric math problem embedded in a social negotiation, an LLM's architecture is biased toward generating safe, highly probable middle ground tokens. Like, let's split it 50-50 is probably an incredibly common phrase in negotiation training data.
Exactly. They generate the familiar phrase rather than solving the novel problem. Which brings us to the fourth and perhaps most alarming failure mode. The researchers identified referential binding failures.
Right, we noted earlier that overdraws where the agents demand too much and the round is annulled happen 15.7% of the time, despite the cheap talk.
Yes, but here is the crazy part. In 52.3% of those overdrawn rounds, the agents actively used positive agreement language in the text chat right before they submitted the bad allocation.
They literally generate phrases like deal or sounds good or I confirm our plan. And then immediately after, they output a JSON purchase decision that completely violates the agreement they just made.
It is wild. The paper highlights two distinct variations of this. The first is proposer amnesia. So an agent originates the idea for a split, the other agent agrees, and then the first agent completely forgets its own idea at the moment of decision.
And the second variation.
Self-commitment abandonment. An agent agrees to a collaborative plan, but at the decision step, it abandons the shared plan and just reverts to a greedy strategy that maximizes its individual points, triggering the overdraw penalty.
So what does this all mean? Are these agents actively trying to deceive each other, or are they just genuinely forgetting what they just said? Is it just an artifact of the architecture predicting the next token?
It is largely not intentional deception. It's a cognitive mapping failure. The AI is operating on two entirely different representational levels. You have the linguistic symbol space, the text generation where it makes the promise.
Right, the cheap talk.
Exactly. And then you have the downstream action constraint, the structured JSON output it must generate to finalize the turn. The LLM fails to bind those two modalities together.
The text agreement basically just functions as autoregressive social lubrication. It outputs deal because statistically that token follows a proposal in its training corpus, not because it actually updated its internal action plan.
Exactly. The language model lacks a global state that syncs the semantic promise with the execution layer. It highlights a massive vulnerability. They can easily generate the syntax of agreement without possessing the underlying semantic commitment to the action.
Wow. Okay, so we have a clear picture of the bottlenecks. They anchor on early ideas because it's computationally easier. They default to lazy 50-50 splits due to probabilistic biases, and they suffer from referential binding failures because they decouple words from actions.
Yes, and the obvious intervention seems to be fixing the information asymmetry. They are failing because they have hidden agendas, right? So the researchers designed a final intervention to test exactly that hypothesis, the full transparency condition.
They took the top-performing pair, Cohen 3.5 Flash and GPT-5 Mini, and explicitly revealed both agents' complete secret project specifications in the system prompt before the cheap talk even began. Complete transparency.
Which should theoretically solve the perfunctory fairness issue immediately. If they can mathematically see each other's exact needs, a 50-50 split is demonstrably irrational.
Did it work?
It did solve that specific symptom. The rate of lazy 50-50 splits dropped dramatically, from 5% to just 1.7%. When the asymmetric needs were transparent, the shortcut was easily avoided, and it also reduced the overall number of overdraws.
Boo UT. And there's always a but. The overall optimum rate, the frequency with which they actually achieved the perfect mathematical solution, did not reliably improve. Wait, if they literally have all the answers up front, how do they still fail to get the optimal score?
Because, shockingly, that stubborn anchoring behavior actually doubled. It spiked from 23.1% to 46.7%. Having more context seemingly made them worse at negotiating.
They just locked onto the first idea even harder.
Exactly. This raises an important question. If they possess perfect information up front and they have the raw reasoning power to find the solution, why do they anchor twice as hard on suboptimal plans?
It proves definitively that the coordination gap is not simply a matter of information asymmetry or bounded reasoning. The bottleneck is the interactive process itself, the actual mechanics of joint plan formation, maintaining a commitment and executing it.
Knowing what to do in theory is fundamentally different from coordinating that action across multiple turns of dialogue. When provided with all the information upfront, they locked on to the very first semi-workable plan they calculated and stubbornly refused to adjust, even if a superior joint plan was achievable through further dialogue.
Information exchange alone is insufficient. The hurdle lies entirely in dynamic grounding. So just to summarize our journey on this deep dive, we took a stack of research on state-of-the-art Gen AI, and what Yao, Zhu, and Hawkins have demonstrated is that while LLMs can flawlessly crunch numbers in a static vacuum, they stumble spectacularly when forced into the interactive reality of dynamic grounding.
They rely on computational laziness, they default to probabilistic fairness over actual optimization, and they break verbal promises because they cannot bind their words to their actions.
And for you listening, as we move into an era heavily reliant on autonomous agents, this coordination gap is a massive hurdle we have to watch out for. We're envisioning ecosystems where AI might negotiate freelance contracts, book flights, or manage complex supply chain logistics on your behalf.
And if an agent can convincingly generate sounds like a plan, I will allocate the funds in an email, but then execute a completely conflicting set of API calls because it failed to dynamically ground that commitment, the fallout will be massive.
It is not enough for an agent to be smart in a vacuum. It has to be truly collaborative.
Which brings up one final thing to think about. As we study these failure modes in artificial intelligence, it offers a really striking lens through which to view our own human behavior. Consider your own negotiations, whether navigating a complex project at work or attempting to divide household responsibilities.
Oh, we fall prey to the exact same traps all the time.
We do.
Yeah.
How often do human endeavors collapse not due to a lack of intelligence or hidden information, but because of a fundamental failure in dynamic grounding? We sit in the meeting, we nod, we utilize positive agreement language, but we walk away with entirely divergent mental models of what we just committed to doing.
We anchor on our initial assumptions. We opt for the lazy compromise to avoid friction.
Exactly. We fail to rigorously bind our verbal agreements to our subsequent actions. So perhaps when these models confidently output deal and then completely wreck the shared budget, they are just reflecting the flaws in our own communication data a little too perfectly. Maybe they're acting a little more human than we'd like to admit.